Let's put this second derivative test to work, and we're going to locate some relative extreme values. In this case, I'm working on 286. I'm going to do number 61 here. It's from our practice exercises. So the idea is this. We're going to start by taking the derivative, and f prime of x is pretty easy to find. We're just going to use our power rule, and I think you'll agree that's negative 2x plus 2, and it's easy to find the critical points for that function. You set negative 2x plus 2 equal to 0, and you find out that x equals 1 with a little algebra. So the critical point is x equals 1. Now here's where the second derivative test comes in. We don't necessarily have to make a sign diagram like the first derivative test. We can simply find the second derivative, double prime there. Oh goodness, I'm just making it worse. And the second derivative is just negative 2. And then remember that when the second derivative is always negative, this function is always concave down. So the shape is going to be something like this. And that makes sense because we know this is a parabola. And what that tells us is that if we have a critical point and we plug it into the second derivative and the value is negative, in this case it's always negative, that this critical point must be a relative maximum. And in this case, we also know this is a global maximum. But we have a maximum at 1, comma, plug 1 into the original function to figure out the y value. And negative 1 plus 2 plus 4 is 5. So we have a maximum at 1 comma 5. Turns out that's the vertex of the parabola. So that's a very simple case of the second derivative test on a parabola or a quadratic function. The second derivative was always negative, so any critical point we were going to find was going to be a maximum. Let's go ahead and look at a more complicated example next. Problem 65 from the same section with the same instructions is a little more complicated function. It's a cubic, but our strategy is going to be the same. We're going to start by taking that first derivative and we're going to locate some critical points. So f prime of x, we're going to use that power rule that we know about. This is going to be x squared minus 4x minus 5. And again, it's a polynomial, so the critical points will be at the zeros of the polynomial. So I'm going to set x squared minus 4x minus 5 equal to 0. And you can use your favorite technique for solving this quadratic. It looks like this factors pretty easily, so I'm going to use factoring and the zero product property. This factors as x minus 5 and x plus 1. And so by the zero product property, that's a zero there. By the zero product property, I either get x equals 5 or x equals negative 1. Those are my two critical points. So again, we're going to use the second derivative test to see what's happening at each of these critical points. First, we find the second derivative. In this case, it's going to be 2x minus 4. And then what I'll do is I'll plug each of my critical points into this second derivative. First, I'll plug 5 in. And when you plug in 5, you get 2 times 5 minus 4, that's 10, minus 4, which is 6. Since the second derivative is positive, I'm just going to make a note. This is going to end up being a relative minimum. Let's go ahead and test negative 1. F double prime with negative 1 plugged in. That's going to be negative 2 minus 4, which is negative 6. And I'm going to make a note that because that second derivative is negative, that point's going to be a maximum. Let's go ahead and find those extreme values for this minimum at x equals 5. We have to plug 5 back into the original equation. Now I already did that on my calculator, so I guess I'm cheating a little bit. But you can do the same thing. You can plug 5 into f of x way up here. And when you do that, that minimum will be located at 5 for the x value, and the y value is negative 115 over 3. And then we could do the same thing with negative 1. You plug negative 1 into the original function, and this maximum occurs at negative 1, and then the y value is negative 7/3. So that second derivative test, you take each critical point, plug it into the second derivative, and then look for the value, the sign, I should say. Here we had a positive 6. That told us that we had a concave up function, so we have a minimum. And here we have a negative 6. That told us that we have concave down, which is a maximum. And then you can compute the y values by plugging it into the original function. Hopefully this helped send home the idea of using the second derivative to find extreme values. Good luck and keep up the good work.